Okay, so hello, I'm Aria. I'm sorry for my voice. I had a severe flight delay and only got 1 hour of sleep today, but I will try to do my best anyway. So, yeah, I'm from Corporate Foundation and wanted to present a library, a really nice library that we made for hardware, like transactional hardware for Amaranth HDL. So Amaranth HDL is a really nice language. It's a Python-based DSL. It had a workshop on last OrConf, so you should definitely check out the language too. So I will introduce you first to the concept of transactional hardware. So let's start with a method. A method is basically an action that can execute in hardware in a single clock cycle. It can take some input, produce some output, and they have concept of readiness to execute. So they can only run if they are ready. So maybe let's show that on some example. So everyone favorites example, FIFO queue. So what you can do with FIFO? You can read from it, write to it. So read would be ready when the FIFO is not empty, and it returns data from the FIFO, and writes does the opposite thing. So yeah, that's basically it, and everything of that is encoded inside the method. Okay, so now the actual transactions. So transactions can call method and depend on the methods that they call to execute. So they are atomic. So in a given clock cycle, all methods needs to be ready for the transaction to execute, and they also execute in one clock cycle. So it may be easier to see on an example. So a very simple example, we have two input queues, one output queue, and we have a simple transaction that just adds the value from the queues together. So that's how you define a transaction. It's based on a Python context manager and things that are under transaction. It just takes the methods that are actually used inside of there. But everything else, I think, it's straightforward here. And so let's imagine you would like to add a counter of executed operations to the transaction. So as I said, it's based on context managers, and it's like guarded transactions, so it's very easy. You just add a synchronous assignment in there, and it only will execute if the transaction will run. So if both of the input FIFOs are ready and the output one has space in it. Okay. So now let's see how to define a method. So we need to provide what arguments, what signals does it expect as an input, as an output. Both of them are optional. And you just define a nice Python method with actual signals as an argument and some return value. But it needs to execute in a single cycle. If you would like multi-cycle operations, then the common pattern to do that is to provide like two request and get result methods and some logic to derive their ready signals. Okay. So the next concept are conflicts. So let's imagine you have that huge operation that takes all of the space on your FPGA, and you can only do like one instance of it. And you have two sources that you want to execute the computation. So that creates a conflict between two transactions. Or another example of conflict is two different transactions wanting to write to a queue. And in this case, the Transactron automatically generates a transaction manager that inside has so-called schedulers for each set of conflicting transactions that will select one to execute. So if one of them is ready, it will be selected. If both of them are ready, there is some arbitrary priority selected. You can tune that, but yeah, so that's the logic that will be generated. So the called method will be run if either of these transactions are ready, and in this case, the transaction one got priority. And you don't need to think about that at all. You just call the methods from two transactions, and it all happens like in a generated output Verilog. And also, if you are not confused enough for now, there are methods can call other methods. So this huge operation can depend on some read from a FIFO queue, And you may want to take data from the same queue from some other transaction, so you don't have a direct conflict on one method with other transactions, but it all executes in one cycle, so actually all of these 3 transactions are in conflict to each other, and this all is handled automatically. So another nice example of what of simplifications that are made for you. So let's take a pipeline as an example. So you can implement pipeline like that. So some combinational steps that have FIFO that has like depth of 2 FIFOs between them, just to like split the combinational paths between them. And if you have a large timing budget, you might want to merge 2 steps together. So that's like literally 1 line of code change. You change FIFO to connect, and it will just execute in 1 cycle. So it's really nice to experiment with. So like summarizing why transactional hardware, you don't need to care about latencies and conflicts. Like, it's not only about conflicts, but also about readiness of data sources. So you can have transactions that depend on different set of data sources, and they will always execute correctly, and they will always execute as soon as some subset of input that they is available that they need. And this can really avoid you writing complex run conditions, and what is worse, when modifying the code slightly, you need to think how to update all of them, and in this case, it's all done automatically. Another benefit, you have clean interfaces, so you can just look at the method definition, at the module definition, and you see what method it provides, so what are the functionalities, actions that you can do with it, so the FIFO has written right. This is an example from our processor. So this is like an announcement. So you have some register writes, reorder buffer writes. You just see what the module, what to expect from the modules. And the most important one, it makes programmer more happy. It's really nice to write in practice. Lets you avoid some bugs. It's not a Verilog. And some of you talked about BlueScape Verilog. So for those who know BlueScape Verilog, that was our main inspiration, obviously. We expanded the concept pretty much, but mainly in concepts like not more advanced ones, not displayed on this presentation. But from the main differences, we have way more flexibility. So we are not a language. Transactron is not its own language, but it's only like overlay on Amaranth language. So it still operates on all primitives of the Amaranth. And registers are not transactional. They are just it's up to you how you write the code. They are just plain Amaranth registers. So there are many less constraints in general. So like the example of flexibility would be that you can do some nice stuff like read method that depends if the write is called in the same cycle, something like that. So you can really do anything and like override the registers in there in the order of program. We also have a library with all of already made parameterized transactional structures. So like FIFOs, all of these connectors. We have hardware logging. That's really nice concept. And test-bench infrastructure, so you can generate like async processes that simulate models. And okay, it's all great into examples, but have you tested this out in practice? Short answer, yes. That's like an exported schematic of design that we work on that is purely transactional for like last 3 years. You can see it's quite big. Is it useful? Yes, I use it as a tablecloth on conferences. So it is useful in practice. But more seriously, it's our modular out-of-order RISC-V processor that we work on. Everything is transactional in there, like no cheating inside. And the library was actually originally made to support development of the processor. It was later separated from the processor itself. So I have now some nice demo for you. I need to find it and transfer it to the screen. Was it 5? No. Yes. Okay. So I have a board in here, and it runs our core block processor, and it runs Linux on it, and yeah, just ignore all the errors. And that's the end of the presentation. So you get a link to the library here. We have nice getting started guide if you want to check it out. We would love to hear your feedback. Here is how to contact the foundation and just see what we do, mainly on the Fostodon for now. There are some updates and link to the processor core. And we are looking for contributors to both of the projects. So if you are interested, just find me later on the conference. I will be happy to chat about everything here.
Thank you.
Is it general enough to be worth considering an RFC to Amaranth core?
It's really a huge library, and we do some hacks on Amaranth inside, and actually some features on the Amaranth where I think it's safe to say we're inspired by our internal hacks in this library. So I guess some of the features get slowly migrated, but I don't expect the transactional one to be there. But it's like really nicely integrates as an overlay to a language. So I don't think that's a problem. And the core blocks project is actually, I think, for now, the biggest project using the Amaranth language. So
I think you're right. Yeah, I mean, I maintain awesome Amaranth, so I've got a. Yeah.
So worth checking it out.
Yeah, Rob Taylor / awesome Amaranth if you want to go see the list of projects. But I think it's slightly out of date at the moment. But yeah, great. Good to see like the hacks get in at least. That'd be really cool. But it's something I've been wanting to play with for ages. I just like, what were the main uses for it being like outside of a processor design use case? What would you say, like sort of places where you'd see a good use of it?
We used it in other cases too, and generally we found that it makes designing like any more complex hardware way easier, just because of this no need to think about latencies, validity of source data. And also the interfaces, the main benefits I covered here, that's really helpful basic for any hardware, especially when you have some pipelining and multiple sources of data inside.
Very cool. Is it quite easy to use with the new streams interfaces?
Yep.
Cool. I'll definitely play with it. Thank you.
Thank you. I'm impressed that UTF-8 works.
Hi. You had on your introductional slide something that all operators are executed single cycle, correct?
Sorry, yeah, methods and transactions are all single cycle, need to be executed.
So if I have, let's say, an operator, I don't know, a complex coordinate, square root, these kinds of things, and then an adder somewhere else, is then the slowest defining the speed of the
No, that's, then you would not do this as a one method, but there was actually one slide about it. You would create a module with two methods, like a request to start an operation, and then another method that you will get a result from. And you just control readiness of the methods. So if the module is not busy, then the like request for operation is ready. You can request the operation, then it starts. Both of the methods are not ready. When it finishes, you can get the result from the get result method, from the second one, and it clears the busy flag, something like that.
Would this imply also that I can do operator duplication for the slow data path, for the slow operators? Like Catapult C does that. If I have, let's say, an expensive operator in terms of latency, I can add multiple of them to get the throughput right, and then I can schedule to multiple.
We have in transaction, like in the transactional library, so the wrapper, like another wrapper on the transactional core itself, we have a nice like modules to create multiple methods, like an array of methods. So that's created in mind for superscalarity, but I think that fits in here. So that's the duplications with nice wrappers.
Another exciting discussion for the coffee break. If you want to join in, get together with Aria and Dirk. Thank you very much.
Thank you.